Okay, so we're at section 6, logarithmic functions, and we're at the second objective. The student will be able to use and apply logarithmic functions and properties of logarithmic functions. The first objective was that we learned about one-to-one and inverse functions, and a function can have an inverse if it would be one-to-one. And the inverse is what you get when you switch x and y. You switch up the independent and dependent variable. The logarithmic function with base 2 is defined to be the inverse of the one-to-one exponential function with base 2. So here is the exponential. The base is greater than 1, so it's increasing as we read from left to right, and of course passes through 0, 1. And it is one-to-one. It passes the horizontal line test, so it does have an inverse. So to get the inverse, of course, we are going to switch x and y. And that's a statement of the inverse, because that means the same thing as a logarithmic equation. There are no algebraic techniques that can be used to solve for y, because that's how we like it. We like y equals, so does our calculator. So we simply call this function y the logarithmic function with base 2. The definition of this new function is that log base 2 of x equals y. That's a function, right? Y equals, and then there's some kind of function of x. And that equation is true if and only if x equals 2 to the y. So it's just another way to write. It's another way to write. Start with this and switch x and y. This equation here is just another way to write it. It means the same thing, okay? And usually we've got y on the left, so we do have a new function of x. Log base 2 of x. But it's just the function that you have gotten when you've switched x and y. The inverse of an exponential function is called a logarithmic function. That's what undoes exponential. For b greater than 0 and b not equal to 1, so it has to be positive, but it cannot be the number 1. Here is our definition of the logarithmic function. These two things are equivalent. Y equals log base b of x, x equals b to the y. In other words, the log to the base b of x is the exponent. A logarithm is an exponent. That's what it is. If you're wondering what it is, what is a logarithm? It's an exponent. The exponent to which b must be raised to obtain x. The logarithm is the exponent that you have to raise the base to get, well, this thing right here, which is called an argument of the logarithm. An argument. So you've got your base. Got your base. Now you've got an argument, which is just an input. Okay, an argument, that's a kind of a calculator way to say input. The domain of the logarithmic function, okay, so we've got this new function here, and so it's got to have a domain, It's the set of all positive real numbers. The range is the set of all real numbers. Okay, so important fact, it comes up in homework problems in a certain way. So you'll need to make sure you know this very well. Domain is the set of all positive real numbers. So here you've got the familiar graph, y equals 2 to the x, an exponential function, explodes for positive values of x. And then, well, what do we know about inverses? They are reflections of each other through the line y equals x. And so that's how the logarithmic function, which is the inverse, the one that also has base 2, looks. Y equals log base 2 of x is the blue graph, and that's the reflection of the black graph through the line y equals x. Of course, that y equals log base 2 of x just means the same thing as x equals 2 to the y. Switch x and y. And the tables, you can see that you really have inverses because in the tables you've got the ordered pairs reversed. And for the logarithmic function, it says x equals 2 to the y, which of course is just y equals 2 to the x, but with the x and y switched. But this equation over here on the right, of course, just means y equals log base 2 of x. The domain of the logarithmic function y equals log base 2 of x is the same as the range of the exponential function y equals 2 to the x. Why? And I invite you to pause the video to consider this question. Why is the domain of the logarithmic function the same as the range of the exponential function? It's because the domain of the logarithmic function, what is the domain? The set of x values. Well, we're switching x and y here. So set of x values, if we switch x and y, that's the set of y values in the inverse. Well, the set of y values is the range. And so the range of the exponential function is the domain of the logarithmic function. The range of the logarithmic function is the same as the domain of the exponential function. Again, why? Well, the range of the logarithmic function, the range is the set of y values, but if you're switching x and y, now you've got the set of the x values, and that is the domain of the exponential function. Okay, and just to be clear, let's think about what these sets exactly are. Domain of the logarithmic function, if we're talking about the logarithmic function, the domain is the set of positive real numbers, and of course that is the range, the set of y values of the exponential function, because the graph is entirely above the x-axis. Range of the exponential function, well, we know what that is, a set of all real numbers. No, I'm sorry. Well, it's the same as the domain of the logarithmic function. The domain of the exponential function is the set of all reals. Any real number can be an exponent, negative infinity to infinity, and that is the range of the logarithmic function. Another fact, if one graphs any one-to-one function and its inverse is on the same grid, same set of axes, the two graphs will always be symmetric to one another with respect to the line y equals x, which of course we have seen. So the line y equals x, identity function, here's your logarithmic graph. Here's a sub-objective. The student will be able to evaluate logarithms. Study the examples below. You should be able to convert a logarithmic into an exponential expression or equation and vice versa. So here's a logarithmic equation, and well, the definition of the logarithm showed how a logarithmic equation is related to an exponential equation. And when you say log base 4 of 16 equals x, the 4, the 16, and the x are related, so that if you were to write an equivalent exponential equation, 4 to the x equals 16. Okay, so that's the equivalent. And well, that just means that x equals 2, right? Because 4 to the second power equals 16. Okay, so it's as if you're looking at a logarithmic equation and you're trying to figure out how it would look, how the exponential equation would look, think of it this way. Think of there being, you've got log base 4 of 16. Log base 4 of 16. What number is that? Let's evaluate this logarithm. Okay. Well, what I would do is try to imagine a little equation within the logarithmic expression. It's kind of using your imagination. After all, the logarithm is an exponent. So right in here, we're going to make a little equation. Okay, we're going to put a little tiny box and a little tiny equal sign and ask 4 to the what power equals 16. What goes into the box? Well, it's 2, right? 4 to the second power equals 16. Therefore, the value of this logarithm, the value of log base 4 of 16 equals 2. $125 equals 5 to the third. Okay, how do we write that as an exponential equation? Well, it's good to remember a couple of facts here. One fact is that the base of the exponential equation is the same as the base of the logarithm. Okay, so the base is the base. The base of the exponential is the same as the base of the logarithm. The base is the base. So we're going to have as a base of our logarithm, base 5. This is going to be log base 5. So the logarithm that's in the equation is going to be base 5. Okay. The other thing we have to remember is, the thing that we keep saying over and over again, and it'll sink in at some point, is that the logarithm, the log, is the exponent. The log is the exponent. The exponent. Okay? So apparently the log is 3 then. That is the logarithm. 3 is the logarithm. The logarithm is 3. Now, logarithm, of course, has no meaning without an argument, and by process of elimination, we've got to say that the argument is 125. Argument is 125. So the equivalent logarithmic equation is log base 5 of 125 equals 3. The power to which you have to raise 5 to get 125 is 3. So if you remember those two facts, you can write the logarithmic equation every time without any ambiguity. It'll be completely clear. Of course, we could have done the same thing for number 1. The base is the base, the logarithm is the exponent, 4 to the x equals the other thing, 4 to the x equals 16. I guess these two statements are more useful if you're going this direction, though. You're changing an exponential equation to a logarithmic equation. Square root of 81 equals 9. How would you write square root of 81 equals 9? Well, first you want to remember that the square root is the 1/2 power. And of course, it's powers that we need because the logarithm is a power. We're dealing with powers, and so we want everything as powers or exponents. And so those radicals, we can't really deal with those radicals. We always want to put everything in a fractional power. So, it's good to remember that because of the old rule which says that the 1/nth power of something is the nth root of that thing, the 1/2 power is the same thing as a square root. And so instead of a square root here, we're going to write the 1/2 power. Well, now we've got an exponential equation, and we're able to convert it to a logarithmic equation. The base is the base, and the base is 81, so that's a big base for a logarithm. And the exponent, the logarithm is the exponent. The exponent is 1/2, so that's going to be equal to the logarithm on one side of the equal sign. And the other thing is the 9. That's by process of elimination, that has to go into the position of being the argument of the logarithm. So log base 81 of 9 is equal to 1/2. Log base 3 of 1/27. Okay, what is that? Well, we want to think of 1/27. It'd be nice if we could think of it as an exponential with base 3, and you'll see why in a moment. Well, the 27, we can write the 27 as an exponential with base 3. The 27 is the same thing as 3 to the third. Okay, so this 27 right here is the same thing as this 3 to the third right here. And of course, since we're dealing with logarithms, we're dealing with exponents. And if we're dealing with exponents, we're dealing with laws of exponents. And you may or may not remember the meaning of a negative exponent. A to the negative n equals 1 over a to the positive n. Well, we've got 1 over a to the positive n, and so what we're going to do is change the sign of the exponent, and so we have 3 to the negative 3. Well, what is the power that you have to raise 3 to get 3 to the negative 3? 3 raised to what power equals 3 to the negative 3? Well, it's negative 3. Okay? Using the definition of logarithm, you can solve equations involving logarithms. So solving equations, that's a big objective here. Let's rewrite it so that there's more room here. So with our little examples, tiny box and our little tiny equal sign. Log base b, we're evaluating a logarithm right now. We're getting a value or a number. Well, little log tiny base box, 3, little tiny equal sign. Well, remember what goes into the box? What goes into the box? B raised to what power? Little tiny box. B raised to what power? Little tiny equal signs. 1,000. Well, which I just messed up. They're telling us it's 3. Okay, little tiny box, little tiny equal sign. So 3 is going into the box. Now I'm not thinking about a log. B to the third equals 1,000. So well, then what's b? We're solving for b in this equation. We're actually solving for the base 3 to the negative 3. Okay. Well, bases are the same. It's easy because are equal. So obviously the thing actually the third power of something. Box is that negative 3. The cube of something, and it's actually the cube of 3. And so what we're really saying is that b to the third is the same thing as 10 to the third that goes into the box, and is that negative 3 cubes. So the value of this logarithm is 2 things raised to the same power 3, and the two expressions are equal to each other. Therefore the bases have to be equal, and b has to be equal to 10. Log base 6 of x equals 5. Okay, so now here is really the best problem, the best example that we've got here. Here's an equation that you're going to have to be able to solve in your homework. And, well, what you're going to do is write the equivalent exponential equation. 6 to the 5 equals x. Well, what is 6 to the 5? 6 times 6 times 6 times 6 times 6 are 7,776. So the solution to this equation is 7,776. In each of the above, we converted from log form to exponential form and solved the resulting equation. Okay, we took y equals log b, m, and n are positive real numbers, and we wrote b not equal to 1, b to the y equals x. The base is never allowed to be 1 for the exponential or for the y equals x, and p and x an easy equation for us to solve. Then we have these things true. Okay, and why are they true? Well, think about the equivalent exponential equation. B to the 0 equals 1. Okay? Tell me you remember that. Okay? Raise any number to the 0 power and it's 1. And so therefore, whenever no matter what the base is, if the argument is 1, the value of the logarithm will be 0. Log base b of b equals 1. Why is that? Well, because it doesn't matter what b is, it's always going to be true that b to the 1 equals b. Okay, anything is itself raised to the first power. Log base b, b to the x equals x. Well, if you think about the little tiny box and the little tiny equal sign, that's going to be true. B to the x equals b to the x. And of course, the equivalent exponential equation is trivially true. B to the x equals b to the x. It's kind of like, well, that log base b of b in there in number 3, I mean, that log base b of b without the 1 equals x. So it's kind of, in your imagination, you kind of imagine this x being, set free by the removal of log base b of b, which is 1, and you just come out with the x. Now, if you think about it, you realize that what has happened in number 3 is that what always happens with inverse functions happened. That is that the logarithm undid the exponential. Of course, those two things are inverses. Logarithms are exponential. So you could think of it this way too. Cancel the logarithm and the exponential, and you just get out the original input, right? You take an x, you run it through b to the x, you run the result through log base b of the input, and you get back the original x. Well, the same thing happens with this. Cancel, cancel. The exponential is now undoing the logarithm, and you're getting the x out of it. Other rules of exponents, very significant ones, particularly number 7, but 5 and 6 are huge. Sometimes they call them laws of logarithms. And this tells you what to do with the log of a product. And this tells you what to do with the log of a quotient of two things. And then number 7, that's the big one. That's probably the reason why we use logarithms and why we make it part of our course. Log base b of m to the p. Now look at what happened on the other side of the equation. It turned out to be p times the logarithm. So it is as if we have taken the p, the exponent of the argument of the logarithm, and thrown it down front as a cofactor. And that's a very useful property because a lot of times we have things up here in the exponent, like variables, like x, that we really don't want up there. We have now a way to throw them down out of there. Sometimes
It's good
our
to put some of these
logarithmic
things in
equation
words.
is able
Okay.
to be made into the
These are
form
the same four
of
properties
two
that we
logarithms
just
equal
were
to each
looking
other
at.
with the same base.
Number 5
and
says
so then we're
that
going to
the
be able to
log
set
of a
the
product
exponents
is
equal to each other. Okay, now log of a product. So
It's
is it
kinda
like
like
you're canceling the
the
logs?
root
in
of a
that
product?
case? The root of the product is the product of the roots. Is the log of a product the product of the logs? Sometimes you get a property like that. The power of a product is the product of the powers. Is the log of a product the product of the logs? No. The log of a product is actually the sum of the logs. So multiplication in the argument actually shows up as sum of two logarithms. And of course, a lot of times we like to go this direction with it, write the sum of logs as the log of a product. We, obviously need to go either direction with this. And we kind of understand why this property is true if we remember that the logarithm is an exponent. And we remember the a to the x, a to the y equals a to the x plus y rule, that when we multiply exponential expressions with the same base, we end up adding the exponents. Well, if that's true, if the log of a product is the sum of the logs, what should the log of a quotient be? Well, the log of a quotient is going to be the difference of the logs, number 6. And so that's a lot of properties of logarithms. I encourage you to do lots of problems in order to learn these properties, maybe even more than are assigned. And in that way, we'll be able to master these properties.